Welcome, folks. Talking about advanced applications of integrals today, in particular, talking about moments and centers of mass. The main motivation for this discussion is to imagine a plate occupying a region R in the XY plane. And then imagine that we can take our magical mathematical scissors and cut out this plate. We'd like to know where to place a point in order to balance this plate. So here's a rough stylization of that region R. And here I'm thinking about this point P as being the center of mass of that plate R. So we'd like to know where, if we were to hold it on our finger and balance it, for instance, where we would put that point. Okay, we'll start off with the law of the lever, thinking about discrete points, and then we'll see how that idea can be generalized into balancing a plate as we suggested in the motivation. So here's the law of the lever. Suppose that you have mass 1 and mass 2 balance the distance d1 and d2 from some focal point. It turns out then that m1 d1 is m2 d2. So this is the old teeter-totter idea. You can imagine that if one person is heavier than the other, you'd have to place the fulcrum off center in order to balance the weight of one person on the weight of the other. So again, that's called the law of the lever. Now, we can stylize this on a number line by sort of thinking about one of the masses being at point x1 and the other at x2. So here I stylized placing mass 1 at position x1, mass 2 at position x2, and let's just suppose that the center of mass is there in the middle. Now we can relate x1 and x2 from the law of the lever. So here again is our center of mass at x bar. We know that the location x bar is d1 past x1, and we know that the location x bar is d2 from x2. That allows us to express d1 and d2 in terms of x1, x2, and x bar. Now, the law of the lever, m1 d1 equals m2 d2. When we substitute d1 and d2 in, we can solve this for x bar. And when we do that, we get an equation for x bar in terms of x1, x2, m1, and m2. So here's that equation of the center of mass. It's m1 x1 as m2 x2. Now, if we think about m1 x1 as the moment of m1 with respect to the origin, and m2 x2 as the moment of x2 with respect to the origin, we can sort of stylize this center of mass. And that stylization tells us that you can express x bar as the sum of the moments divided by the sum of the masses. Now, this idea generalizes to placing a whole bunch of masses along the number line. So if we place mass 1, mass 2 out to mass n at positions x1, x2 out to xn, the center of mass is still the sum of the moments divided by the sum of the masses. Okay, so again, we're thinking of mk xk as the moment of the kth mass about the origin, and mk as the mass of the kth mass, obviously. So we're adding up the sum of these moments and dividing by the sum of the masses. This can be generalized to the xy plane too. So if we think about placing n masses at n points in the xy plane, we can similarly define the total mass of the system as little m, and then think about the moments of the system about the x and y-axis respectively. So the moment about the y-axis sort of tells us how much the mass of the system is balanced or disproportionately balanced along the x-axis, so how much it tends to swing around the y-axis. And similarly, the moment around the x-axis is how much it tends to swing around the x-axis. So here are those expressions. M is the total mass. The moment about the y-axis, again, incorporates the x values because it tells how proportionally or disproportionately we are about the y-axis. Similarly, the moment about the x-axis tells us about the y values, about how much we tend to swing about the x-axis. Once again, the center of mass is exactly what we expect it to be. That center of mass is exactly the moment about the y-axis, so sort of incorporating those x values divided by the mass of the system, and similarly, the moment about the x-axis divided by the mass of the system. Okay, so let's do an example. Here is 3 masses placed at 3 different points in the xy plane. So again, we'll sort of find those different moments and then write the center of mass as the sum of the moments over the sum of the masses. Okay, so here we see the total mass of the system. The total mass of the system is 10. We see the moment about the y-axis. The moment about the y-axis is 14. Again, that can be interpreted as a positive number due to the fact that we're more likely to rotate, we're more imbalanced to the right side of our XY plane than we are to the left side. We can see the moment about the x-axis as 10, and again, this can be interpreted as the fact that we have more mass in the upper half plane than the lower half plane. So again, the x and y coordinates of the center of mass are just the sum of the moments divided by the sum of the masses. So the x coordinate of the center of mass, m sub y over m, 1.4. The y coordinate of the center of mass, m sub x over m, so 1. So we expect the center of mass to be, somewhere right about here. Again, with x coordinate of 1.4 and y coordinate of 1. And we see the center of mass here at 14/10 and 8/10. So here's that center of mass with x coordinate 1.4 and y coordinate 1. And we can think of this system as being equivalent to having one mass with 10 units of mass pointed exactly at 1.4, 1, so an equivalent system. Okay, let's go ahead and think about now balancing a plate in the XY plane. So we'll think about a plate of constant density rho occupying some region R of the XY plane that goes from 0 to f of x in the y direction and from A to B in the x direction. Now we can go ahead and think about the kth rectangle that approximates the kth strip of this region. And again, here we're not writing this down officially, but we're thinking about dicing up the interval from A to B into n subintervals of equal width delta x and so on and so forth, so that this rectangle goes from x sub k minus 1 to x sub k. Now, we expect that the center of mass of this rectangle ought to be right there sort of in the middle. So that's what we've written here, that the area of this rectangle ought to be just the base times the height. Of course, the mass is the density times the area, and the center ought to be exactly halfway between those x values and maybe halfway up on the rectangle. So again, here's that rectangle, and the centroid of the rectangle is right there at xk star and 1/2 f of xk star. Okay, from that, we can think about adding up all of these centroids and center of masses and letting n go to infinity to find the total mass, the moment about the x-axis, and the moment about the y-axis. And here are those expressions. So again, we get the mass by looking at the integral of the density times a little bit of area. We get the moment about the y-axis, thinking about the mass times the x coordinate in the sum. This becomes an integral. And similarly for the y coordinates, the moment about the x-axis. Once again, the center of mass is just the sum of the moments over the sum of the masses. And here's what we get in those integrals. Again, the moment about the y-axis, telling us how much things tilt in the x direction, is given by the integral from a to b of rho x f of x dx. The moment about the x-axis, telling us how far things tilt in the y direction, is given by rho times 1/2 f of x squared integrated from a to b. And then in the denominator, we have these integrals that tell us the mass. Okay, so let's go ahead and find the center of mass for this region R bound between 0 and e to the x on the interval from 0 to 1. So we'll do this like we did before by just writing down the mass of the region and finding those moments. And we'll just assume that it has some constant density rho. So here's our total mass of the system. Total mass of the system is the integral from 0 to 1 of rho e to the x. So we obtain rho times e minus 1. The moment about the x-axis, sorry, the y-axis is the integral from 0 to 1 of x e to the minus x dx. Of course, there's an integration by parts here. I won't go through that in all of its gory detail, but I'll trust you to do it. We end up just with rho there. The moment about the x-axis is given by a similar integral here, 1/2 e to the x quantity squared, which we end up with the end of the day, rho over 4 times e squared minus 1. So here's the center of mass of the system. The x coordinate is m over m sub y, which simplifies to 1 over e minus 1. Sorry, m sub y over m. And the x coordinate is m sub x over m, which simplifies to 1/4 times e plus 1. Okay, folks, one last comment. If the region is slightly different, namely that the coordinates go from G to F instead of 0 to F, we have just slightly different equations for the moments and center of mass. So there are a couple examples like that in the book, and I'll let you just have a look at those. All right, folks, hope you've enjoyed this video on moments of center of mass. Have a great day, and we'll see you next time. Bye-bye.